Okay, cool. So my name is Moshe Zadka.
I'm Kurt Rose.
And today we're going to talk to you about introducing best practices into your legacy code. So let's first go over what we're going to cover. We'll be very careful to define our terms. What's best practices? What is legacy code? We'll try to outline the goals. Where are we trying to go? We'll go over the typical problems that will stand in your way. We'll talk about both technical solutions and social solutions to these problems.
So first, to define our terms, what do we mean by legacy code? First, we mean code that's important. It's code that you're putting a lot of effort into maintaining and extending. It's important to your business. If it wasn't important, you would just let it go and you wouldn't be investing more resources into fixing it up. It's also code that's hard to replace. If it was easy to replace, it wouldn't be a big deal. You would just replace it. You wouldn't be trying to invest time in fixing it up. It's generally bad. So this means that maintaining and extending the code is taking more and more time. If it's old but not bad, great. You're doing something right, just keep on doing what you're doing. And it's old. If you have code that you find is important, hard to replace, and bad, causing you problems, and it's not old, then you've got a problem with your current development processes. And first, you want to stop digging your hole any deeper before you worry about dealing with the mountain of code that you've written in the past.
So why does legacy code tend to be bad? Well, the common utterance of, man, what idiot wrote this code, is okay as an exclamation. It's not the reason. It was probably written by people who are around as smart as you. It was written by smart, hardworking engineers trying to do their job. So that's not the reason. But it quite possibly is the case that they might have been inexperienced in the tech stack. One popular reason why that happened is because the tech stack was new at the time, so there were no experienced people at the time this was written. They might have been rushed. The company might have deadlines, like there was a demo, there was an important company launch, there was an investor date, whatever it was. They might have had serious deadlines, and they couldn't take the time to write really high-quality code because they needed to get it out the door by a specific time. And it's quite likely they were working on a different assumption than you. One popular assumption that was probably different between the time they wrote it and the time you're dealing with it is scale. When it was new, it was probably not used by a lot of people. Now, it's great that your business is growing. It's great that a lot more people are using it. But this is a very different situation than the people who originally wrote that code were living in.
So we're going to try to improve the situation by using best practices. What are we trying to achieve? First, we want the code to iterate faster. So it should take less effort to write new features going forward. We want to fix the latent bugs in the system, and we also want to introduce fewer regressions. Basically, the goal is to be able to move fast without breaking stuff. So what do we mean by best practices? Best practices are basically a social construction. They're common knowledge of the way to approach problems within a given community. They may not be the optimal solution to a given problem, but they're probably also not the worst solution to a problem. Also, by using sort of standard approaches, you get the benefit of having a lot of other people that have faced the same problems. You can probably find good documentation, blog posts, stuff like this, and you get a lot of transferable knowledge. As people enter and leave your team over time, they sort of know what to expect out of the code. On the other hand, best practices still require thought. This isn't cookie cutter approaches that you can just apply to a code base without taking a careful evaluation of its current state.
So what are we trying to avoid in this project? We definitely don't want to halt development. This thing is important to the business. Probably new features added to that are important to the business to make more money. What you definitely can't tell everybody to do is just be hands-off for 6 months, not touch it, not develop any new features, well, we fix everything. That would be great, but you just can't afford it. No business can. You also don't want to confuse and annoy the other engineers involved in that code base. That basically leads to a lot of problems, both socially, and probably it's not going to be good for the code either. And you definitely do not want, while you're introducing best practices into this code, to cause outages. That is not just bad for the business, which is obviously bad. You'd never want to cause outages. It will also get this project canceled. The second time there'll be an outage, and the reason will be, oh, we were trying to fix some weird unit test case, that project is going to get canceled. It's not giving any reasonable feedback, and it's actually causing problems right now. So that is definitely something you really want to avoid.
We also have some non-goals. These are things that you shouldn't care about one way or the other. So this talk notwithstanding, the goal definitely isn't to make a cool blog or talk about how you used a certain technology. Also, we definitely don't want to upgrade to all the new buzzwords. In addition to architecture by Hacker News article being a bad idea in general, specifically when you're working with a legacy code base, you know you're dealing with something that's been around for a few years. It's probably going to be around for many years into the future, so it pays to be a little bit conservative in your technology choices so that you don't pick the wrong hot new technology and end up maintaining something that's been deprecated and abandoned for a long time.
So what are we trying to achieve? Well, we want to be able to take advantage of better practices. This used to be a good way to read a small file into memory in one go. This is not bad code, but it's kind of error-prone, it's kind of annoying, and there's a much better way, which is this, which you can do with newer Python. You want to be able to take advantage of that because that code is nicer and it's harder to introduce problems into it.
Also, you want to introduce developer efficiency tools. Over time, workflows have gotten better and better. So one tool you should consider is Tox. What Tox is going to do is automate virtual env construction during your tests. So this helps avoid that issue where somebody's adding a new dependency on some library and it works on their machine, they push it up, but they forgot to push the new dependency into the setup PY. So somebody else downloads it, it doesn't work on their machine, it doesn't work on the CI, or maybe it doesn't even work in the live environment. So Tox is going to ensure that your tests are always run in a completely clean environment with no accidentally installed modules. You also want to use unit testing and coverage. That's again going to give you more confidence that the code is running correctly, which is going to let you move faster. And also you should consider static checking. There's Pylint and Flake8 that have been around for a while that can help you find bugs in areas of the code that aren't covered in your unit tests or maybe hard to reach areas. And there's also static type checking like MyPy that seems to be the new thing in the Python community. So that's also worth considering.
So you also want to move to current or at least support the dependencies. If you're still on Python 2.6, you want to move to 2.7. 2.6 is not getting security updates. So if you're stuck on 2.6, 2.7 should be your highest priority. If you are on 2.7, remember, it is getting security updates until 2020, which is great, but much closer than it appears. Also, not getting any new bug fixes. So if you are on 2.7, you probably want to move into 3.6. And remember, 3.6 is not going to be maintained forever. As you move into 3.6, make sure you already have a plan on how to move to 3.7. You don't want to cause this problem again. And of course, other than Python, which is quite possibly your biggest dependencies, you're also depending on a lot of libraries, and also on those libraries, you want to move to current versions or at the very least supported versions of these libraries.
So one common problem you'll encounter is that the code has gotten kind of too big. So the way that you get here is that the modules and functions are laid out in a certain way when the code is first written, and then bit by bit you're adding more functions. So pretty soon you add just one more class to your module and it's become 10,000 lines. You're adding just one more piece of functionality to a function and pretty soon it's thousands of lines long. You're adding just one more argument or just one more if branch into your already kind of twisty structure. And the way that these happen is it's always easier to just add another little piece of code than it is to think about how to break it into two sort of equal sections. And in a legacy code, these have had time to grow quite big.
The other version, as we alluded to earlier, is that you're stuck on old libraries. Maybe you're using Explicit 900, which was a great version for its time, but now they fixed a lot of problems, and you probably want to move to newer Python, to newer Twisted. And of course, sometimes the library you depend on is just dead. It's old, and there are no new versions. So that's quite a problem.
So something else you might find is deprecated idioms. In previous versions of Python, this used to be the best way to create a set. You call the set constructor and you pass it an iterable. But now we have a set literal syntax, so you want to move to the newer, simpler idiom.
And of course, some things were never a good idea. But maybe the people who wrote it didn't know, or maybe they were in a rush. And that command failed because the user wasn't in the database, so you just return the default output. But now, of course, it's sometimes failing because the database connection has gone away, or the database is missing, or the database is slow, and you're then giving default output, which of course means that when database connections from one single machine get outed, all the requests routed to that machine all get the default name. That's a lot of fun to diagnose, because the way that the problem is getting reported is some users complain that the name is not correct in the application. You have no idea which users, what it happened, or the reason is actually that the underlying problem that was just masked by this plain don't accept. Plain don't accept is very dangerous. In those cases, you want to realize which exception was actually raised and should have been cut, right? Maybe the user not found exception, maybe the IO error from the command, maybe the OS error from the command. And of course, that will actually take some digging to fix, but you want to do it. You want to catch only the specific exception that you accept and let the other ones actually cause a traceback in the application. That is a production problem that you do not want to hide.
Another problem you can have is overuse of metaprogramming. Python is great that it has all kind of metaprogramming facilities built right into the language. You can write a lot of cool tools natively in Python that you wouldn't be able to do in other languages. But on the other hand, it's very, very easy to reach for that powerful chainsaw metaprogramming when you're really just trying to scratch your back, and that's very dangerous to do. So in this case, somebody found that they were writing a initializer that was extremely repetitive. They had self.a equals a, self.b equals b, self.c equals c. I'm sure anybody who's used Python for any length of time has written code like that. And they said, aha, I can make this a little bit shorter if I just use this cool locals function and pass that to dict update, and now I don't have to write this dumb repetitive code. But of course, they also got an unintended side effect, which is that the locals didn't just include the arguments to the constructor, it also included self. So they tried to clean that up by saying del self.dict self. In general, this is a bad idea. I believe that the function call is the single most powerful, best abstraction in all of programming. And the key to the abstraction of the function call is that the local scope goes away when the function finishes executing. By using metaprogramming in this way, you've broken that abstraction. So for this specific problem of having a repetitive initializer, we can recommend Adders. It's a great library, and it will automate construction of that initializer. No tricky metaprogramming involved, and hey, look, it's even fewer lines of code.
So another problem that often happens is if you have very tight integration. And this is kind of the stereotypical thing where you call a constructor from the constructor. You have just bound these objects very, very tightly together. You cannot have a foo without the actual concrete class bar. That probably gonna mean that unit testing is gonna be hard. But not just unit testing, any other usage of foo. Maybe in the staging environment you want to construct bar with a staging parameter. Hey, guess what? You can't. Maybe you want to pass something that's like a bar but wraps it so it logs. Hey, guess what? You can't. That is usually bad. That is usually a bad sign to construct stuff from the constructor. And if you're already using Atlas, as you should be, you can just make a dumb initializer and use what I like to call a named constructor in Python. That is how the pattern usually looks like, where you still have the old functionality. When you just want foo to be constructed with a regular old bar, you can just do that, right? That's very easy to search and replace throughout your code. But now when you want to unit test foo, you can just pass something different, some awk object, some fake object, and pass that to foo, and you can just use the init method as usual.
Another problem that you can find in large old code bases is what we call a floating abstraction. This basically means you built it, but nobody came. You made a nice abstraction, but it didn't really fit other use cases. So in this case, we see there's this getAddress function, and it actually has 4 distinct different ways that you might turn a logical name into a network endpoint that you can connect to. So how do we get here? Let's go back in time. It started out simple and it made sense. We just want to use DNS to look up the name, but then we also need to specify a port. So we got a nice, simple, straightforward function. But then there was a problem. It turns out that DNS was too slow for some reason. So someone came along and added this data structure that holds the service IP addresses, so that way it's not doing a network call to resolve the IP address. However, it was too hard to track down all the things that were being DNS looked up, so we still leave that as an alternative fallback. Then something else happened. There was an issue where we wanted to serve multiple services from the same host. The problem with them all using the same port is that they can't bind to that port. So we needed to add another different data structure that allow you to specify a unique port for that service. But at the same time, we still have some other services that don't really need the unique port, and maybe we weren't sure exactly where all they were coming from. And of course, there's still the DNS path as well. Then, some of the things got deployed to IPv6. The thing about an IPv6 IP address is it has colons in it. So you realize that actually the data structure never really should have been mixing IP and port together. So we add another data structure that keeps the IP and port separate as it should have been from the beginning, but at the same time, we're not confident that we found all the places where those old addresses might be floating around and those places where we have an IP but no port floating around and all the places that it might be using DNS. So the code has become very, very complicated. Basically, we have many different abstractions for all doing the same thing. And over time, we're just adding more and more of these abstractions. So really, there should have only been one way to go about it. This is like Zen of Python. There should only be one obvious way to do it. However, as each issue arises, it's easier to just add another special case instead of going back and migrating everything to a new case. Properly solving the problem requires understanding the old use cases, which is hard and you may not have time for, so the code is gradually decaying.
So another problem is what we like to call the missing abstraction. So the missing abstraction is when you have a lot of functions that look a lot like bad copy-pastes of each other. And again, it was all done with a series of rational steps. First, the user only had strings objects in it, and that was great, except we needed the age to be an int because we had to compare it for 13 to 13 for legal reasons. So we had to do it very quickly. So we had like this weird hack of getAge, which did the cache lookup and the conversion to int, so that we make sure that we cut all the cases and we could reliably compare it. Now, someone saw that we already did that, and when they wanted to actually have the address object replaced instead of the address string, which does some like the weird zip code normalization, they just added another function which got the address and then automatically ran the parser on it so that we immediately have access to the address object. And then someone saw that we did that, so that when they needed a phone number standardized in a way that we can actually dial out, so add the area code that's needed and so on, they just added like this function. As you can see, things are starting to look not that good. The function is actually called parse number, the attribute is called phone, and the function that is called get phone number. Of course, there's nothing keeping those things in sync, right? So in those cases, you want to see that if you can move to like some data-driven approach, right? Maybe ORM, or maybe some other pluggable brains thing, where you have a class with the attributes, with a proper init, and when people add attributes, they properly add whatever converters they need, and nobody is really surprised, and everybody does things the same way, and you don't have to keep writing the words cache lookup user, comma, which will probably at some point someone will misspell, and then we'll find weird problems later on.
So these are both illustrative examples of a general problem that you find a lot in large old code bases, which is an intent usage mismatch. The code had original intent. There was meant to be just one function that was kind of throwaway. It was meant to be just one abstraction that was going to handle all of the necessary use cases. But then over time, that intent got violated. Maybe the assumptions were wrong. Maybe the people that needed to extend the code didn't have time to really understand the code that they were modifying. But what these have in common is that debt naturally accrues. Your technical debt is kind of getting compound interest because the more people make ad hoc modifications, the easier it is to make an ad hoc modification. The more that an ad hoc modification that makes the code larger seems like the right thing to do in that code base. Keep in mind, these examples were easy mode. These are basically examples of how you get to those 10,000 line modules, multi-thousand line functions. These are the kind of problems that grow and grow and grow and overwhelm your code base unless you take the time to fix them.
So we're stuck with all these problems. How are we moving forward? Well, what you want to avoid is having a minimum viable product. A minimum viable product is a great idea when you don't know if a product is needed or exactly what it needs to do. But you know that it's needed, the business is depending on it, and you know what it needs to do, exactly what it does now, modulo maybe some bugs. But if you start by replacing the easy 80%, you have done nothing but add another parallel system, and you have no idea how it is to get to the last 20%, which of course is the hardest 20% to actually get to. So just because you can write something that like does most of the traffic, then that doesn't mean you've achieved anything. So it's really, really easy to say, oh, you know what, I'll just like change this function over. But that's basically how you get to the floating abstraction case, where you keep adding these minimum viable projects, and they keep layering on top of each other as each person comes and adds their own minimum viable products on top. You want to notice the skulls, right? You want to notice when people have tried it before. You'll often see them in the code base as a half replacement attempt that never actually got all the way through. If everybody who's tried going that path has died, you should think very carefully about what kills them and how to avoid it. You should not go down that path. You will probably die. Remember, they were no stupider than you. They were very smart engineers who were exactly as hardworking as you. Notice that. Take a step back and think, what am I actually going to do to validate that this approach is actually going to work for 100% of the use cases? And like I said, they were pretty smart people. Maybe the reason they haven't completed it is because they were out of time or because the project got canceled. See if you can find a partial solution that you can finish. It's much less nice for your ego. You're not going to innovate, but it's probably much safer. The person who did that knew a lot about the code. They learned a lot about the code as they made that change. They probably know more than you if you are new to that code. Now, the reason people do these like minimum viable products, the reason they're not confident of getting to the last 20%, often it's really hard to test 100% of the cases. There's always this weird niggling code that you're just going to leave for later because it's really, really hard to add. And that's going to be the corner that eventually metastasizes into a new problem that's exactly of that sort. So you want to improve your tests. Tests are basically what's going to validate you. Tests are going to be your way to actually fixing the problems and not adding to them.
So maybe you're working in a large old code base and you find that you have good tests available. Lucky you, that's great. Use the good tests. In addition to being a good way to validate that your changes aren't breaking things, the tests are also a good guide to the intended public APIs and use cases that the code is meant to have. Maybe, on the other hand, you find that there are no automated tests yet. Okay, in that case, we can make some concrete recommendations. First, keep in mind as you're deciding what things are most important to test, that the purpose of the test is to support future development. Don't worry about testing cases that you're never actually going to reach. Don't worry about checking fixing the O of n squared thing that's only ever going to get 10 inputs. If you don't have a test runner yet, we recommend PyTest. It's currently the most widely used test runner, and in the interests of using best practices, that's going to be the easiest one to find documentation for. Also, as we said earlier, Tox is a good tool. In addition to automating setup of virtual envs, it can also automate running your tests under multiple versions of Python. So that's going to make it easier to migrate forward when you eventually need to. And keep in mind that you're only interested in the environments that your code actually runs in. If your development environment is Linux, you don't really care how your code runs under Windows or OS X. Maybe there's some weird file path error that happens under Windows, but it's not really going to matter because your code never runs there. So what if you have bad tests? There's different ways your test can be bad. One common way is if your test is change prone. So in this case, we have a unit test, and it's checking that the function concretely calls sort and sys.standardout.write with the exact arguments and in the exact order. So this is bad because every time that you change your code, you also have to make a complementary change to your tests. And so it's taking a lot of your time to maintain those tests. In addition, your test isn't really testing the purpose of the code, it's testing what the code does. So you may not have thought about what the purpose of this code is, and your test may not actually be protecting you because whoever's calling this code might be counting on something that you're not really testing. You're just testing that the code is as it is. Another way that tests can commonly be bad is if they're flaky, if they sometimes work and sometimes don't. One sign of this is if you find random sleeps sprinkled through your tests, that's probably a sign that there's some kind of a race condition in the code that you don't quite figured out. There's a missing join or lock somewhere. In addition to being a pain in the butt, because you can be in these situations where you rerun and rerun and rerun the CI until it gives you a green light, this could be hiding latent issues that are only going to happen in live that your tests might never exercise. So if you have bad tests, our recommendation is just delete them. They're not doing you any good. Go back to the no test case and start over.
So we just told you what not to test, and we told you to delete the current test, and that includes gives you a lot of downward pressure on the number of tests. Unless you introduce a countervailing upwards pressure, you're never going to write more tests. And the best upwards pressure is unit test coverage. And the only number you should shoot for is 100%. And there's two reasons. One is the simplest test, literally checking that 1 is equal to 1, and importing the module usually gives you 60–70% testing depending on the code. Because guess what? It's executing all your constant statements, it's executing all your function definitions, it gives you all your class definitions, and most Python code is exactly that. So, woohoo, I'm 60% of the way there. No, you're not 60% of the way there. You have just tested that your module imports. Guess what? If it wasn't importing, you'd probably have noticed it by now. So it's not giving you any useful thing. The other thing that any number other than 100% gives you is weird action at a distance. Imagine you have a function, and you add a new branch to that function, and you unit test that branch really, really well. You have not made things any better, right? You've added a new branch to a function. Hopefully that branch was necessary. You have not made the old code in the function any more tested. But suddenly, the average testability of that function has risen, say, from 0% to 50%. That's great, except you haven't done anything useful testing-wise to that function, right? 100% is the only number that doesn't have this weird action at a distance. How do you measure percentage? Do you measure it by how much the line is executed? Do you measure how important it is? 100% is 100%. It's everything.
But Moshe, are you saying that we need to spend maybe 3 or 4 times as we did writing the code in the first place to try and get to all those weird niggly corner cases where some OS error or some weird kind of socket error that isn't often raised gets handled? So if you have things that you have decided rationally not to test, that is a perfectly rational decision. You probably know what you shouldn't test. Maybe there's a defensive code of a defensive code that is literally currently impossible to get. Maybe it's an error that you don't care about. Maybe you just don't have the time to write a test for. You don't want to say, well, we have to write a test or we can't ship this feature. Pretty soon you're just going to lose 100% unit test coverage. Just be explicit. Tell people in the PR that you're not covering that. And the way to tell people in the PR that you're not covering that is to add pragma no cover. The coverage module knows how to ignore those lines. It will not go below 100%. But now you've made everything explicit. You've told the people reading your code that you are not unit testing it. People can ask you why. And you can say, well, I don't have time. They'll ask, well, can you create a ticket? Sure, I'll create a ticket. That's fine. I'll make sure that I get to it later. Can you explain why it's a defensive case of a defensive case and why it's hard to read? Sure, I'll write a comment for that. If it confused people reading your PR, it's probably going to confuse people who will read the code later. As we said, if it's legacy code, it's probably going to live long past you as well. So it's probably going to live long past the time that you and everyone who read your PR are on the team and quite possibly on the company. But that pragma no cover will stay there forever as a warning sign. Anyone changing the code under that knows that they're in dangerous territory. If the time has come to change that code, they know there are no unit tests. And they can make a rational decision. They can make a rational decision to write the unit tests. Great. They can make a rational decision to manually test it in their environment because it's not that important. They can make a rational decision to send an email to QA to make sure they'll doubly cover that the next release coming out. They know what the situation is, but now you've told them what the situation of the code is, and you've let them make an informed decision. Well, and especially with all this code being in these weak nooks and crannies that are very, very hard to reach, you probably want some lean checking. Lean checking is a good way to make sure that your code is kind of okay. It won't find all the bugs, of course, not the logical bugs, but it will find some issues, and it will not have to execute, so you get that for free. But Moshe, I've run Pylint on my code before, and I'll get more warnings than there are lines of code in the project. If I have this big 10,000, 100,000 line legacy code base, are you saying I'm just going to get buried under 100,000 lint violations?
Well, you probably want to judiciously configure the rules. One thing that a lot of people do, and it's actually a great idea, is to blacklist all the rules and then whitelist them in one by one. That will make sure you're not going to add any rule that is not actually paying its rent, in the sense of like the aggravation from having to avoid it is actually giving you usefulness. You probably don't actually have to make sure that nobody ever calls a function with more than 3 positional args. It's probably kind of okay to call something with 4 positional args. Your code will not break. However, the rules you do add must actually pay rent, and you must make sure that the way they're paying rent is by preventing the merge. You should not be able to merge lint failures into your production code. That defeats the whole reason of using lint.
So are you saying that we should one by one add a new lint rule and then go through the whole code base and fix all of those violations before we merge the code?
So no, you have to grandfather existing violations, because not doing that, touching all the files that have current violations, is going to introduce a lot of version control noise. There's going to be a lot of things Git has to track suddenly for not really good reasons. The problems might have been there, but probably are not. Probably that code has been in use for a while and it's probably kind of okay, most of these violations. Touching a lot of files is actually pretty dangerous. Not only is it dangerous, you have just made Git blame useless. Imagine that, for example, someone called a function with x+1 instead of x because it was preventing an outage because they needed the extra headroom. Well, there was also a space they did it because it was preventing it was preventing an outage, and they did it at 4 a.m. and they fat-fingered the space. Now, their name is on it. They didn't add a comment because it was 4 a.m. and they were preventing an outage. So the only thing that that line has going for it is that the name of that line, on that line in Git blame, is the name of the engineer who actually made that problem, who actually fixed that problem. Now, sometimes you're lucky. Sometimes the engineer is still in the company. Maybe you're really lucky and the engineer is still with a team. You can go ask them why they needed the +1 if you're confused by that, if you're reading and you're making a weird change. But if you were so eager to remove that space from the end of the line, guess what? You have signed that. Now your name is there. Now you have no idea what that +1 is doing. You have no idea that it prevented a crash at 4 a.m. And when people come and ask you, hey, why is that 4 a.m.? I don't know, I just removed the space, man. So you have just removed very, very useful information from that code. And of course, hopefully the person coming to ask you is not just going to assume that nobody knows and that +1 was probably added by some idiot who didn't know what they were doing. They will look through Git log. Well, guess what? You're not the only one who added a new lint rule and then fixed everything. Everyone else did as well. Now your Git log for every file is full of fixed redundant spaces, fixed redundant new lines, added new lines where you had to do that. That's not that useful, and now the change that actually fixed the production problem at 4 a.m. is buried under 3 pages of useless Git log. You're also causing a lot of spurious builds. It would be really nice if build systems knew how to ignore these things, but they don't. So now you have just made your CI system churn like hell. Now you might think that's not a big deal, except everybody else with really important changes are now waiting on everything, because of course these things touch all the files that they rebuild, everything that they rerun, all the tests, which now mean that these changes are taking really long time, they're really stressing out your CI system, and everybody else is waiting. And you might think, you know what, I'll just add some more resources to the CI, fine. But you know what other things happen with legacy code? Well, it's possible that the code that had all these spaces and bad violations, it's quite possible whoever built the build system wasn't that careful either. They were the same person probably, right? So quite possibly the build system is not as reliable as you might hope. Now, it might be okay most of the time, but guess what? When you're adding 1,000 builds to the system, now you're definitely going to hit every single one of the problems, which is possibly mean that a bad build will actually get released into production. So, bad. And, will actually cause an outage, which is really bad because we said we don't want to edit. And even if the build system is perfect, the other thing that is not perfect is you. When you remove the space from the end of the file, are you really sure that you pressed X once and not twice, and also remove the comma? There was, of course, between 2 strings, so Python is not going to complain. It's just going to add these 2 strings together. Now the function is going to get with 1 less argument. That's not even going to cause a failure for most of the time because there was a default argument, that most of the time was kind of okay. So now you have this weird problem where sometimes people have these weird concatenating strings that was kind of okay for most of the time because the strings were actually close together, except sometimes, and now you get one of these really, really hard to diagnose outages, and you cause it, and you have no idea because you do not know what this code does. It's a legacy code that was written long before you, and you have no idea what's going on there. So I just told you not to fix everything. You do want to make sure that you're in a ratchet system. You want to make sure that while it's possible to add lint violations if judiciously needed, it's explicit, it's careful, it's not easy. But it's very easy to remove any grandfathered violation. If you're already touching some code, if you're already taking the risk of modifying that, and presumably you're already testing it and you're already thinking carefully about what it's supposed to do, that is a good time to fix these violations. You want to make that process as easy as possible.
So what if you need to upgrade Python? If your legacy code is on an old version of Python, that's often a common case. At Shopkick, we're still dealing with Python 2.6. At PayPal, I was dealing with Python 2.5 until 2015. So you're going to need to upgrade the version of Python. And if your code isn't on an old version of Python, well, sooner or later it is going to be. So first thing, if you're on any version of Python 2 other than the latest version of Python 2.7, consider going to the latest version of Python 2.7 as a stepping stone. That's going to give you access to a lot of libraries that are in the same version as Python 3 that you won't be able to access in 2.6, so you can make a smaller, safer change. If you're on Python 3 and you're looking at upgrading to the newest version of Python 3, go straight to the newest version of Python 3. There's no point in testing an intermediate version. So the two versions that make sense today is CPython 3.6 or PyPy 3.5 compatible version. Don't worry about how your code runs on any other version. Now, Python and the standard library are pretty good at maintaining backwards compatibility. The biggest challenge is probably going to actually be library compatibility. So let's talk about upgrading libraries. When is it time to upgrade a library? Well, obviously first, not before you can upgrade the library. Why can't you upgrade a library? Well, it could be that you're on a version of a library, or you're on a version of Python rather, that's so old that your library has dropped support for it, and there's no longer publishing new versions. They're no longer supporting your version of Python, so you're stuck. You can't upgrade until you upgrade Python. Also, you don't want to upgrade until after you have to. Why would you have to upgrade a library? Well, the exact inverse situation can happen. You could be on a version of Python that's or a version of a library that's so old that it came out many years before the current version of Python, so there is no build available for the new version of Python. So what if you can and you don't have to? Now you've got a more complicated decision to make. In general, you want to upgrade reasonably soon after a stable release. That's going to give you advantages because every time you face a bug with a library, you're not going to have to dig through a changelog to see if you're dealing with a known issue that's already fixed. Also, it's much easier to submit patches and sort of maintain a local fork temporarily while you've fixed something locally if you're working from the latest version than if you're working from some old version. At the same time, you want to avoid churn. Every time you upgrade a library, you're causing a certain amount of risk to your system, so you don't want to upgrade too quickly. Also, ideally every library would be perfect, but it's possible a new version has some issues, and you want to let somebody else run into those issues. You can wait till people have been using it successfully for a little while. Ideally, you want to upgrade libraries one at a time to minimize risk, but sometimes you can't. Maybe libraries depend on each other, or maybe versions of Python are forcing you to upgrade many libraries at once, or maybe you just don't have time. You don't have enough releases to do them one at a time, so you need to do several at once. But if you can, one at a time is great. So how do you go about upgrading the library? First, definitely consider binary wheels. Binary wheels haven't been around that long, so if you're dealing with an old code base, it's entirely possible that you were building from source in the past, but these are going to make your life a lot easier. You definitely don't want to be worrying about whether you have the right version of libxml when you're trying to compile something. Binary wheel lets you just have the compiled once on one machine instead of every time on everybody's machine. You also want to make sure that you have good tests. You want to test all the usage of the library to make sure that you're not introducing any regressions when you do the upgrade.
So I don't get it. Like, why do you need to test that carefully? People mostly use Semver nowadays, so you can just know that if you're updating a patch release, you're only going to get bug fixes. If you're only updating a minor version, you're not going to get any backwards compatible. You don't have to worry that much.
Well, first off, we're talking about nowadays, but by definition, we're talking about old code. So maybe the library is doing the right thing today, but was it doing the right thing many years ago when the current version that your code is using was created? That may not be the case. The other problem is that what exactly is the public API that is deserving of a major or minor version bump is a little bit fuzzy. For example, are the exact types of the exceptions raised in different error conditions? Is that part of the public API? You might have a different opinion about that than the library maintainer. Finally, again, we're talking about dealing with like a large old code base. So you probably aren't 100% confident that in some corner there isn't some util.py that's calling some helper function that's reaching into the guts of an object of this library in some unclean fashion that's going to sync you when you do the upgrade. So in general, don't count on version numbers. The only information you should take is that a newer version number is a higher. Everything else, you want to test and treat every upgrade as a source of risk and make sure that you test all of the uses. Finally, what if you're using a library and you find out that it's actually gotten to end of life? This is an unfortunate time, you know, I guess a time of mourning for the library that's passed. Well, maybe the library's been forked. So for example, if you're using PyCrypto, it hasn't had a release since 2014, which is bad for a security library, but there's PyCryptodome, which is API compatible and is currently maintained. So great, you can move to the forked version. In this case, your job is to just find the fork. But maybe it's just dead, and there is no version to go to. This is unfortunate. You can find a lot of these on Google Code, for example, libraries that just nobody's bothered to pick up. You have a couple choices. One is you now own that library internally, and you have to make fixes and extensions as needed. Another is you need to try to find an equivalent library to migrate to. Unfortunately, there's no real good story here. This is one of the hardest problems that you'll face with an old code base.
So if you want to be careful, service-oriented approach makes a great thing. And the reason is one process can only be on one version of Python at a time. Also on Python, one process can only load one version of the library at a time. So if you want to be very, very careful, then when you upgrade multiple processes that are doing different things, then each with different surface area, then upgrading one process is going to be much easier because you only have to update all their libraries and all that code. So basically what this is pointing at is basically what we used to call service-oriented architecture and now has a more trendy name of microservices. And basically you can still do it bit by bit. You can take some chunk of code, move it to a separate process, and then carefully upgrade that, and that will be a much more careful approach than trying to shift all your code over from, say, Python 2.7 to Python 3.6. The other people involved are engineers. You have to make sure that they're going to be on your side when you introduce best practices, and one of the ways to do it is to demonstrate advantages. So let me explain what I mean. On top is the old way we used to write like something simple like a tree visitor. We used to take a callback and then run it through and pass it on to the recursion class. At the bottom is a new way, using a modern iterator. They look kind of the same. The iterator is actually slightly longer. So why is it better? Well, it's better because this used to be how you used the visitor pattern. It's kind of annoying. You have to define a list with one element. You have to call the callback. Then you have to get the stuff out of the element. It's kind of annoying. It's weird. It's not clear what you're doing. This is how you sum things now, right? That's much, much nicer, right? And the thing is that often when you make that change, you should be careful to actually make a couple of the dependent changes so people see why you're doing that. You should actually demonstrate why it's making things better off rather than just making the change and then tell people, hey, everybody, move to my new thing. It's much better. The couple of first changes are better on you. Then you want to make sure that people get the continuing education resources they need. So at Shopkick, we have PyVideo tech lunches where we literally choose a video from PyVideo, watch it over lunch, and then talk about what we learn and how we can apply it locally. We also give dedicated lightning talk. If we see a lot of people struggling with a problem, we'll just schedule a meeting and talk about how to solve it. And we also have an internal blog. That's great because it's way more async than the dedicated lightning talks. And also people who are kind of uncomfortable giving talks can easily contribute to the internal blog. Now, a recruiting blog is great. Your company should probably have it if it's recruiting. But an internal blog completes a different function. You could be much more straightforward about the shortcoming of the problems in the internal blog and how to solve it. And you can refer to specific problems in specific code bases that you're all encountering. The other thing you want to do, if you want engineers to support you, is give them support back. Make sure that you show them how to do things better in the code review. Actually write many lines of code in the code review saying, here's a better way to do that and here's why. That is very useful to people. Also, when they're actually in the trenches, when they're actually showing a problem with something you suggested, you need to actually help them debug that problem. You need to make sure that to show them that you're in the same boat with them. And of course, if you don't want to continuously run from one engineer to the other and help them, you want to have much better automation. So at the very least, you want to make sure that your software developer lifecycle, you can say, it's no worse than GitHub. Now, it can be better than GitHub, but you have to make sure that it's no worse. For example, we use GitLab. GitLab is nice because it has an open source version that is pretty good, and you can easily just install it and run it yourself and not pay anyone anything. You also want to make sure that whatever software development lifecycle you use actually integrates into the CI system. So as soon as people have pull requests, it's getting in the CI, it's getting built, they see the results directly on the pull or merge request. And once they do that enough and they're getting used to that feedback, they'll be annoyed that they have to actually wait for the CI to complete to get any of that feedback, especially if they're trying to iterate a bit faster. So you want to make sure that they have all the tools they need to test locally as efficiently as possible, so at the time they put the pull request up, it's clean. The other people who have a stake in the matter is obviously management. You want to make sure that they're on your side too. Management cares about one thing, return on investment. They're paying a lot of expensive developer salaries. They want to know what they're getting in return. You have to be able to show them. So one way to show them is make sure that gradual changes give equivalent gradual results. What you don't want is a 6-month project that has 0 yield in any possible axis until it's done. That is a good way to make sure that someone says, well, let's just take one engineer off the team to do something really urgent, and soon enough you're left without a team and nobody is actually fixing the code. You also want to be very risk averse, right? Management really cares about outages. If there is a potential change that might cause a risk, maybe put it at the end of the project, not at the middle of the project. Make sure that you're very, very careful with any potential problems, because that, again, can easily sink that project. And you want to measure carefully, not just for the benefit of management. You also want to get that feedback. If you're promising that what you're getting is, say, more developer efficiency or less regression, how are you going to know? How are you going to know if you actually are applying best practices well, or you're just doing things to do things and you're not actually getting any benefit?
Finally, when you're dealing with a big legacy code base, the alternative that you're probably considering is rewriting the whole code. I want to tell you that rewriting is not a panacea. First off, rewriting is not going to be fast. Even if you think it's going to be fast, you're probably mistaken. If you think it's slow, it's probably going to be slower than you expect. There's going to be all kinds of weird details that aren't apparent when you're starting off. Another thing to keep in mind is that for a while, we want to have gradual changes that give gradual improvements. Well, a rewrite is actually going to be a negative at first, because now you have 2 parallel systems, and you also have the meta system who's designed to decide which of the 2 parallel systems should actually be taking traffic at the moment, and that's throwaway code, so that's probably not too well written. So you're actually making things worse until your rewrite is complete. And your rewrite might not quite get done. Maybe people get pulled off for some other high priority project. So now you've got this other geological strata of an 80% rewrite that never quite got finished. I've definitely seen a lot of these in old code bases that I maintain.
So in conclusion, remember, your legacy code is not going to look as nice as code you just wrote with new best practices. It's always going to look a bit old. It's always going to look like it was written a long time ago and adjusted carefully to modern best practices, but not quite.
At the same time, the code can be made better. You can have very old code bases that are clearly old, but at the same time have a good developer workflow.
And we think it's worth the effort. You go through all this effort, we kind of try to explain how hard it's going to be, but it really will make your life better to be on a version of Python that actually has support from the community, say, and be on a version of library that are actually current.
And keep in mind that rewriting is risky, so it's probably worth your time to try and fix up your old code rather than expecting that a rewrite is going to solve all your problems eventually.
Cool. Thank you very much. And I guess we do have some time for questions, do we? Hey, person who's managing that, do you want to line them up or something?
Thanks. Really great talk. So I wanted to, if you can expand what you mean by no worse than GitHub, I kind of didn't get that.
Sure. So a lot of people coming into a company are used to how nice it is to develop on GitHub. Now, if you're coming into a legacy system, it's quite possible that the latest they have is something like Gitolite or like GitWeb, which is really annoying, doesn't support pull requests, and it's just hard to use. It doesn't really integrate with CI systems. So GitHub is a nice baseline. People are used to it, and you want to tell them, well, it's no worse than what you do day to day.
Yeah, another example, when we started at Shopkick, it was extremely hard to create new repos. So that sort of put this pressure on everyone to put everything in one gigantic repo, which is a valid design path. You know, that's how Google and Facebook operate, for example. All their code is in one repo. But in addition to all the business logic code, there's also this directory called Sandbox, which is actually one of the largest directories, and it's just kind of everything from everybody. So there's a bunch of data files, there's a bunch of weird scripts in there, anything that anybody wrote at any time, like somebody wrote something in a hackathon, it's in Sandbox, because it's really, really hard to create a new throwaway repo. And hopefully those aren't called by live code, but they actually are called from live code in just a few cases, you know, but we're being really, really careful, you know, yeah.
So I had a question about adding linting. You said that it's important that it's ratchet, and I don't know what ratchet is. Also, how do you go about choosing which rules to turn on in a gradual way?
Yeah, I can talk to both of them. So ratchet is actually the metaphor is a physical device, one of those things that are easy to turn one way, but almost impossible to turn the other way. And the idea is that you want to make it very, very easy to fix problems, but you want to make it explicit and quite possibly a little bit annoying to add new lint violations. So if someone has time to fix something because they're already in the code, you want to make it easy. How do you choose which lint rules? There's a few things. First of all, think about what benefit it actually will give you. Now, for example, all the space rules I think are really nice because they will stop showing annoying code. And as long as you grandfather properly, it's really easy to just not do that. The other things I like to add are things like unused imports or missing imports, because again, they're really nice to make sure that you haven't done something really silly. You want to look at the rules, and it takes a little bit of, I guess, experience with the rules and seeing how things go and deciding. That's a pretty difficult problem, I have to say. Can you give this one to Anna?
I can tell you right now at Shopkick, the one lint rule we're running in the legacy code base is unused imports, and it's been great. It fixed a lot of bugs.
So can you talk briefly about trying to deal with 2.7 versus 3.6 in terms of your legacy code might be expecting Unicode or ASCII or bytecode. It might be using the old exception hierarchy versus the new one. How do you deal with that in your migrating?
Sure. So there's a bunch of things. First of all, 2.7 actually has a bunch of decent primitives to make it much easier to be explicit. So you can do things like from under in the future, import Unicode literals to make sure that you're 3 compatible. And then the other thing to do is to introduce a 6 library. 6 is really, really good at making it easy to write 2-3 compatible code as you're on your way. And again, a lot of unit tests, and often, again, doing service-oriented stuff so you can move processes over to Python one by one is really useful. You have something to add? Okay, cool. I think there was this person in the back. Come front.
Kind of along the same questions of the previous question about linting. So if linting should always be an arrow that should prevent you from merging the code, but at the same time you want to grandfather in all of the previous violations and ratchet them in, how do you grandfather those in without changing those lines of code, but also enforce that they match it?
I think Moshe's got a very good architecture idea around this.
So there's all kinds of tricks you can do that. But one way that I like is actually when you run the linter, run it, like, I don't remember the exact command in Tox, but the equivalent of minus in front of it in a make file, basically saying the linter should run, produce output, but actually not fail the build. But then compare the list of failures to a list of known good failures, probably fuzzy matching, because you want to make sure that it doesn't check on the specific line number. But then you have a master list of existing violations, and again a little bit of tooling to make it easier to remove things when they are there. So you need to write a little bit of tooling for that. It's often not a lot of tooling. It's basically almost a weekend project. But that tool is going to make it much easier. Some more coarse-grained things you can do is just add at the top of file which lint rules to include and exclude. And again, you have to think a little bit about how actually you do that without introducing a lot of noise into your version control. So that is a good question. That is actually not an easy problem. Unfortunately, linters do not tend to make it easy. So this is something you have to think about. Most linters are written for the use case of someone starting a new project, and you will have to go against the grain a little bit.
While we're on linters, is there a specific linter you recommend?
I guess it's a hard question. I kind of like PyLint, especially if you start by default disable everything and enable things in. PyLint also has a decent plugin architecture. Quite a few PyLint plugins exist. I kind of like Flake 8, especially, again, if you configure the plugins very judiciously. There's actually a new linter that my friend Mark Williams is working on, ablint. I think that's kind of hard to use right now, but it is very aggressive, and especially if you combine it with a good grandfather mechanism, that can find a lot of problems. I really enjoy running ablint on my personal code. But PyLint is probably a safe choice in general.
Oh yeah, I'd say all of them is a good thing to do. If you have a good system for suppressing errors and only introducing errors when you intend to, it's great to run as many linters as possible. It's just like when you're compiling C code, you run it under different compilers, get different warnings, fix all the warnings. It'll lead to the best code.
Cool, thank you all.
Thank you.